Hi, tonight today, we're gonna look at wind energy overview. We're gonna look at an overview from the perspective of renewable energy technology. And here we are in an early December day, and this is the view of my place from my place in Hawaii, just to give you a little bit of that warm aloha sunshine on a cold December day. So this is a wind turbine that used to power my house. And you can see that it's covered with ice, which, this is kind of just an illustration that, wind power, wind turbines have to be very robust devices because they're exposed to all kinds of weather and elements and cold and snow and ice. And they really get beat heavily by the wind because of the fact that the energy in the wind is related to the velocity cube. So you double the wind power, you get 8 times the energy just blasting against that device. And then you double it again, you get 8 times again, or 64 times the original amount you were dealing with. And so the wind turbine has to be able to survive in all those conditions. This is actually a very simple kind of device. So these blades spin. These blades are connected to this metal cylinder. And on the inside of the cylinder, there are wires. The metal cylinder has magnets in it. So when the rotor spins, it spins magnets. When magnets spin next to wires, it makes electricity. And then the electricity has to be connected down this pole, and it has to be connected in such a way that you can rotate this device to face the wind. So there has to be some way of keeping the wires from getting all tangled up or dealing with the fact that this is going to be spinning to face the wind. At the same time, it's conducting the wires down through to the batteries or to the grid. There are many different kinds of wind generators. There's kinds this kind is called a horizontal axis wind turbine because the axis it spins in is horizontal. This is called a vertical axis wind turbine because the axis it spins is this way. And this one spins around like a giant egg beater. There are many, many different kinds of experiments in wind turbine design, but most have all settled on this horizontal axis, 2 or 3 blade, and generally 3 bladed is better, wind turbine design. Here's another one of the horizontal axis wind turbines. And this one is, the design of this one is such that it won't start spinning on its own with these outer egg beater type blades. So you have these other simple blades. This is called a Savonius rotor, and this is called this is called Savonius rotor, and this is called a Darius or egg beater rotor. And this Savonius rotor just catches the wind and starts it spinning, and then once it's spinning, these blades take over and produce most of the energy. This is another novel geometry wind turbine shape, very sculptural. So this one is horizontal axis. It spins around this way. And then there are wires and magnets down here. And you can put this on top of a tall pole. And again, it's beautiful, but it produces very little energy. It's got a very small amount of area exposed to the wind, and that's kind of your collection area. And a lot of these novel geometry wind turbines, especially if they're placed low to the ground. I took this picture actually in Paris. It was in a window. It was for sale, and they just don't put very much energy out close to the ground because there's just not very much energy in the wind that close to the ground. So here's some installed in a sculptural way, beautiful sculptures, and generate a little bit of energy. And I wouldn't mind having one, but I wouldn't want to count on it to provide me with my daily energy needs. So this is one of the Iowa's been a leader in wind power. We've talked about this before, but it's number 1 per capita in the nation. Close to 30% of the total energy in Iowa comes from wind, so we've started to make that transition here. And this is the older style wind turbines. Older style, I'd say 10 to 15 years ago, on lattice type towers rather than tubular towers. Much smaller blade diameters. These blades are black, probably so that the ice will melt off them more easily in the wintertime. Here's took a group of students to see a large wind farm when they were rare up in western Iowa, northern and western Iowa. And we flew our own wind blades there just to see what that was like. And this guy here is now, he's graduated from our program, and he's now the director of a sustainable living center on the island of Kauai. This is, I can't think of his name right at the moment. I'll think of it in just a minute. This is Katz. This is Ben Katz. He went on to get a master's degree in business administration, and just recently got a job at the University of Hawaii, with the University of Hawaii system, running a sustainability center called the Kuhulue's Sustainability Center. But anyway, that day he was out flying his wind turbine blade that he had built in the shop. We've been doing this for quite a while. Here's what the technology looked like in 1941. It was a large wind turbine, 1,200 megawatts. That's 1,250 kilowatts. The turbine we have is only 10 kilowatts. And so this was 100 feet, more than 100 feet, maybe a couple hundred feet in diameter. And it produced power reliably in Vermont. But during this time, this was during the war, and materials were very scarce, and so it was difficult to keep this machine running. And it was at a very good wind site in the mountains in Vermont, and but it just didn't. When the war was over, energy was really cheap, and the country turned away from it. Now, the potential of wind is very large, as we've talked about before. We won't get into the details of this, but the percentage of U.S. electricity that could be supplied by wind of the northern plains and central plains states and southern plains states is huge. Texas alone could supply a third of the energy of the electricity of the whole country just from wind. And this, you add this all up, it's several times the energy requirement for the whole country. And this area in this little wedge is often called the Saudi Arabia of wind, because it has the potential to produce more energy on an annual basis than Saudi Arabia does in oil. And it could do this forever, and Saudi Arabia will eventually run out of oil. So, it's interesting to look at the relationship between solar and wind power on a month-to-month basis. And so if you look in the blue line must be wind, and the dark blue line must be wind, and the light blue line must be solar. So this is wrong over here. But if you notice in January, a lot of wind. February, a lot of wind. March, a lot of wind. And then much smaller amount of solar. But then when you start getting into April, again, a lot of wind. But the sun's kicking in here. And in May, it switches, and we've got more energy from the wind, less from solar, and then the wind drops off dramatically. Boom, 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 right down there into August. Solar's really kicking in, and then September, October, November, then it starts to go again the other way, where October's the last month where we've got more solar than we have wind, and then the wind is the dominant source. But you look, it's really beautiful what nature provides us with, because when we start to run out of wind, the solar kicks in. And we start to run around the solar, the wind kicks in. So between the two of them, when we have a source diversity, there's actually a fairly stable quantity of power available. And then if we add to that location diversity, in other words, we don't put all the wind turbines in one place. We put some, in the upper Midwest of Iowa. We also put some down here, because when the wind isn't blowing there, it might be blowing here. And even though we might get less energy, we'll have greater diversity and greater reliability. So source diversity, location diversity, big parts of the renewable and 100% renewable energy future. Basic parts of a wind electric system, we've gone into this. There's some kind of a tail that orientates the turbine to the wind. There's a generator that's magnets and wires that are spun by the rotor that generate electricity. Simple. Then, actually, if you think about it, it's only two moving parts: just the rotor and the magnets, and the whole assembly itself that turns to face the wind. So, just two moving parts. Now, big wind turbines are quite a lot more complex, as some of you have seen at the community college up in Cedar Rapids. And here, you got large wind turbines spin very slowly, so it's difficult to directly connect them to a generator which wants to spin at a higher speed. So you've got gears here, and these gears don't generate more energy. They just translate the slower rotation of this these big massive blades and this big shaft of the wind turbine to a higher rotational speed of the generator. Same energy all the way through. It's just a higher rotational speed and a lower rotational speed here. These devices here are used to turn the turbine to face the wind, and always face the wind. So this has to have a electronic controller back here, which senses the wind speed and knows when to turn the machine on, and also senses the wind direction and knows where to turn to face the turbine into the wind. And so larger scale wind turbines are much more complex, but they're also been, we've been building them long enough now, so they're quite reliable. And as David Osterberg said up at the University of Iowa, this technology is homegrown American technology, which was then taken to Denmark when we abandoned it, and made much larger, much more reliable. And now we sort of buying that technology back. This is kind of the evolution of the size of wind turbines compared to the Statue of Liberty over here. And you can see that, maybe 15, 20 years ago, it was, 750 to 1,000 kilowatts. And I thought, I'd never see a wind turbine bigger than that. Pretty soon it jumped up to almost twice that. And then again, twice that. And then almost again, twice that for the offshore wind turbines. And you can see, compared to the Statue of Liberty, these are quite large industrial devices. Cause some controversy if they're inappropriately placed in communities, because they are big. But again, the beauty is in the eye of the beholder, and I'd rather look at this than coal trains and power lines. Especially if they're appropriately sited in my community. This is I was on a train trip from Montreal to Fairfield, Iowa, and I went through a lot of wind farms, particularly in Canada. Canada's just, Ontario, Canada is, a world leader in wind power. And this was in Illinois, actually, which has a site where there's much lower wind speed than in Fairfield, but they found that it's cost effective even to install wind turbines there. So let's take a look at what that looks like from the train. It's amazing. You can see that on almost as far as you can see in every direction, there are wind turbines. So, it's really happening in terms of large-scale wind power, and we'll learn more about that when Tom Factor talks to us, who's been probably involved in the development of maybe even this wind farm. Here's one in a community, and you've already seen a wind turbine like this up in Cedar Rapids. Again, it's an aesthetic you have to get used to, but I don't find one turbine even in an urban setting to be particularly jarring. So let's dig. That's kind of the general overview. Let's dig deeper into the physics and science and technology of wind turbines. The power that's delivered by a wind turbine is a coefficient of performance, which is the power efficiency of the rotor, times 1/2 times the diameter. Times the density of air, times the area of the wind turbine blade. So this area that the wind turbine blades sweep as they spin, times the velocity cubed. And so two things to note here, two very important relationships, is that the area is actually pi times the radius squared. And so the energy available from a wind turbine is related to the blade diameter squared. So if you double the blade diameter, you get 4 times the power. But the energy in the wind is also related to the wind velocity cubed. And in this case, if you double the velocity, you get 8 times the power. Again, related to the density. Why is the density important? Because the density of air is different at sea level, on top of mountains. And when it's hot in the summertime, it's less dense. When it's cold in the wintertime, it's more dense. And that actually has an effect on the power output of a wind turbine. And what happens here with a wind turbine blade, it's actually an airfoil. And so when the wind how an airfoil works, wind hits right here and it splits. Part of it goes up around here and part of it comes back along the bottom. You notice the bottom is a much more direct route. And, it gets to the back here much more directly. And the fraction of air that splits and goes around the top goes over a longer route. And since we don't create air anywhere here. All the air that comes through here has to come out. So these have to meet back again at the other end. So what that means is, since this is more direct and this is longer, this one has to go faster. And when air moves faster, it spreads out and gets less dense. And so what's going to happen here is there's going to be lift. This is going to pull up. And so wind turbine blades actually fly through the air, and they actually create lift from the flowing wind across them, and that's the effect of the blade on power generation. So let's take a look at the. This was when I did this example. We had a proposed wind generator, which is actually in place now. The Berge XL10, which is one of the most reliable small wind turbines, really one of the few reliable small wind turbines, has a 23-foot, 7-meter diameter rotor, and it has a coefficient of performance of 0.25. So what is the power output of the generator in a 20 mile per hour, 9 meter per second wind? So in this case, remember that formula is the coefficient of performance times 0.5 times the density of the air times the area swept by the blades times the velocity cubed. So if we throw in those numbers, and we're going to use the wind in meters per second, so we're going to have to use the blade diameter in meters, we get 0.25 times 5, 0.5 times 1.223 times the area of the blades, pi, times 9.3. That we get about 4,200 watts. And the typical coefficient of performance for wind turbines is about 0.15 to about 0.35. This is the power curve of the Berge a wind turbine. And what this is showing us is it's showing us meters per second on this axis. So it goes from 1 to 20 meters per second in wind speed. And then on this axis, it's showing us the power that the turbine puts out. So here we are at 1 kilowatt, 2 kilowatts, 3 kilowatts. So what's interesting to note here is if we look at, like, for example, at 6 meters per second, we're at about 2 kilowatts. And if we go to 12 meters per second, we are at 10 kilowatts. Is that right? Yeah, 10 kilowatts. And so you can see that, if we double the wind speed, we get a lot more power out of this machine. It should be 8 times, and that's not working out to 8 times. Let's try something else. Let's try 1 meter per second. No, excuse me, 5 meters per second, and we get about 1, and 10 meters per second, and we get about 6. So that's 6 to 1. So this isn't as there's the efficiency of the turbine and all those other things related here, but this is you can see that it's a very steep non-linear relationship. And you notice what's interesting is it flattens out here. And why does it flatten out? Well, it flattens out because this wind turbine can only, you notice that when the wind turbine when the wind speed is modest, it's only putting out 0.8, 1.5, 2 kilowatts. And when it's putting out 20 miles per hour, it has the potential for putting out much more than that, but it's limited to 12 kilowatts because if it had a 50 kilowatt generator on it, most of the time the wind's down here and it's going to be operating at a very small fraction of that 50 kilowatt generator capacity. So the output of the turbine is actually artificially limited here, and it starts to tip away from the wind. We'll go outside and look at that. We've looked at that, I think, on our original tour, but we'll go out again and look at that, and you can see the mechanism that this machine uses to actually spill the wind once it gets above a certain point, so that it can have a reasonably sized generator that doesn't get overloaded, and it just kind of throws the rest of the energy away by tipping away from the wind. There's surprisingly enough, there is a maximum amount of power you can extract from the wind, and no wind turbine can ever be more efficient than this, no matter what the materials, no matter what the configuration of the machine is, no matter what the fancy kind of blade it has. This is an ultimate maximum, and it's pretty simple to intuitively kind of understand. So with a wind turbine, what you've got is wind flowing toward the turbine from the upwind side, and then it goes through the wind turbine. And how it actually gets how the energy is actually transferred is that the blades slow the wind down. And as it's kind of like when you have a heavy weight and you drop it on your foot and it stops, all the energy that's in the motion of that weight is delivered to your foot. Well, when this wind is flowing and it hits those blades, and those blades spin around and actually slow the wind down just a small amount, then it extracts energy from the wind. So, but the problem is, if you extracted all the energy from the wind, then there'd be no place for the wind to go downwind of the turbine, and you would stop producing power. It's if you had a big, disc of plywood here or something, solid disc, and the wind comes up and stops, you're not going to generate any energy. It stops completely because there's no way for further wind to keep coming through the machine and producing energy. So it turns out, we won't get we won't do the derivation of all this, all the mathematics of it. But if the downstream wind speed is about a third of the upstream wind speed, that's the optimum. If we extract less than that, we won't be getting the most energy. If we extract more than that, we won't be getting the most energy out of the wind. And so that means you can get a maximum of about 2/3, or you can see here in this graph about 0.6. And so what this is showing is it's showing as you continue to extract, to slow the wind speed down. This is a situation where it's actually more wind going through the turbine than you're not extracting all the energy you could, and you keep extracting energy from the wind and you get to a point of a maximum. And then as you try to extract more and more and more, the wind can't get away downwind of the machine, and you start extracting less and less and less and less and less until you get to a point where your efficiency is zero. So what this is showing you is that this is the relationship of the velocity downwind to the velocity upwind. And so when the velocity upwind is zero, then you don't get any. Velocity downwind is zero, you don't get anything. And when the velocity anyway, I think I belabored that point a little too much. And a guy named Betts figured that out in 1919. And so this is the sort of this relationship of how much energy you're extracting from the wind and where you are on this curve of how much energy, how much speed there is upwind versus downwind, is related in a lot of ways to the rotor tip speed. And this is kind of an interesting thing. You look at a large wind turbine that's spinning 18 or 20 revolutions per minute, and you can turn your hand around at 18 revolutions per minute. It's not very fast, but if it's on a 300-foot diameter rotor, think about how far the tip of that blade has to spin around. It turns out that the distance around that outer tip of the rotor as it spins is pi times the diameter. So if we got 300, the diameter times 3.14, it's about 1,000 feet around that rotor. So it's going to go each revolution, it's going to go 940 feet. So if it goes 20 revolutions in a minute, 942 feet each revolution, it's going to go 840 feet every minute. And then the miles per minute, then you just divide that by 60 to get miles per minute. Then you get 3.6 miles per minute. And then miles per hour, divide that again by, multiply that times 60. And you get 216 miles per hour that the tip of that rotor is traveling. So that's really going fast. And the problem is, with a big wind turbine, if it spins faster than that, it could actually reach supersonic speeds, and all kinds of weird things happen to the aerodynamics when it reaches supersonic speeds. So got to be a little bit careful about keeping the rotor tip speed in a reasonable place. And it turns out to get the most, to have the turbine operate in the most efficient range, in other words, extracting the most amount of energy from the wind, you need a proper ratio between the tip speed of the blades. What's the velocity of that tip of the blade as it spins around the end of the rotor, and the wind speed. So the relationship of the tip speed to the wind speed is called the tip speed ratio. So let's look at an example. If we have a 200 mile per hour tip speed, like we were talking about in the previous example, with a 20 mile per hour wind, we'd have a tip speed ratio of 20 miles per hour tip speed to 20 miles per hour wind of 10. And if we look here, you can see that the BETS limit is 60. That's the best you could ever have. And you look at different types of rotors have different optimal tip speed ratios. And when we're talking about high-speed two-blade and 3-blade wind turbines, the tip speed ratio is going to be somewhere between 4 and 6. So a small two-bladed wind turbine is going to want to see a 5.5 tip speed ratio. So that means if the wind is 20 miles per hour, the tip of the blade wants to go 100. Now, one of the problems with this is that means that to get the optimum here, this tip speed ratio, every time the wind speed changes, the speed of the rotor has to change in order to keep this tip speed ratio right here. So this is kind of the peak power tracking equivalent of a wind turbine. It wants to try to track that optimum tip speed ratio by changing the speed of the turbine to as the wind speed, the rotational speed of the turbine as the wind speed changes. And again, it's different for different kinds of wind turbines. And you can see that while the BETS limit is 60%, modern, you don't get much above 45, 48% for practical purposes. And so that coefficient of performance is never usually much above 40 to 50, somewhere in the range of 40 to 50. And you notice that if you have fewer blades, you get closer to the optimum efficiency. You can actually have a one-bladed wind turbine. So you've got a blade that sticks off the one side, and there's a weight on the other side as a counterbalance, and that'll actually be more efficient than a three-bladed, or the American multi-bladed wind turbine is quite inefficient, but it's very robust, and it doesn't have to provide very much electrical power. It just provides power for pumping water. And so it's reliable. It starts at a low speed, and that's why it has those blades. But it sacrifices efficiency for that. So when you have a wind electric generating turbine, then that's why you have those, two-bladed, three-bladed. Again, one blade would be the most efficient, but one blade is very difficult to balance. Two blades a little easier. Three blades, the mechanical engineering problems in balancing that rotor are much easier to solve than in a two-bladed or a one-bladed thing. So that's why, even though it's less efficient, it's easier to manage from a mechanical point of view. And if it turns out that the components for a fixed-speed generator, in other words, a wind turbine that only spins at 1 RPM, are much cheaper and simpler than a wind turbine that spins at different RPM. Different velocities at different RPM. So oftentimes, smaller wind turbines, particularly, they're fairly fixed speed devices. So, in other words, if the optimal tip speed ratio here is around 7 or 8, and we've got this coefficient of performance of 40, well, if the wind speed doubles, then the tip speed ratio is going to go down here somewhere, unless the rotational speed and the velocity of the tips also go up, and then it could stay in this same spot. But if it's fixed and it only spins at one rotational speed, when the wind speed goes up, the tip speed ratio is going to go down. And so that's an issue for efficiency. Now then you can have wind turbines that will be variable speed, and all large wind turbines now are variable speed. It's been found to be worth the complexity to be able to do to vary the speed to keep this tip speed ratio in the optimum spot. This is a little homemade wind turbine on a dump truck, and they're testing it, and you can see this is what the power output was at 5 miles per hour in the truck, at 10 miles per hour, at 22 miles per hour, and at 40 miles per hour. So with a blade diameter of 3 meters, or about 10 feet, at 5 miles per hour it puts out 7, at 10 miles per hour it puts out 60. Again, double it, you get 8 times the power, 22 miles an hour, 630, and at 40 miles per hour, 5,000. So you got a turbine that only puts out almost nothing at 5 miles per hour, 7 or 8 miles per hour. And oftentimes the wind is between 5 and 10 miles per hour, so it's just putting out a little bit. Has the capability at 44 miles per hour of putting out 5 kilowatts. So no turbine is ever designed to operate, at full output at 44 miles per hour, because it's almost never 44 miles per hour wind speed. So these turbines will be designed to operate, maybe start to cut out at about 25, 30 miles per hour, and completely cut out maybe 32, 35 miles per hour. So this 3-meter diameter blade turbine would probably have a 600 or a 700 watt generator on it. Now, some unscrupulous manufacturer could put on a 4 kilowatt generator onto the same blade diameter, but over the course of the year, it would not put out much more energy. You'd think you're buying a bigger machine. Oh, I'm buying a 4,000 watt machine rather than a 600 watt machine. But the output is related to the blade diameter, not the size of the generator. And so even though you've got that big generator on there, it's going to be loafing most of the time down here at 60 to 600 watts. And a 4 kilowatt generator will operate inefficiently there. So you have to match, it's important to match the size of the blades to the size of the generator and the cutout speed of the system. And the cut-in speed makes almost no difference. In other words, well, we'll get into that later. So here are the power curves for some very large machines. This is a 1500 kilowatt machine. This is a different 1500 kilowatt. This is a 1000 kilowatt machine and a 600 kilowatt machine. These would be quite, small size wind turbines these days. Most wind turbines are up in the 2 to 4 megawatts. And, maybe we could find one of these used and put it here at MUM. And what this is showing is the wind speed in meters per second and the power output of the machine. And so you can see here at 10 miles per hour, this machine's putting out 800 kilowatts. And at 16 meters per second, it's rated 1500 kilowatts, and then it feathers back to preserve itself. It actually feathers back, and at 26 meters per second, it completely shuts off because there's just too much energy flowing in the air at that point to be able to make sure that the machine will still be able to survive and operate. So you see they all have the same cutout point, and they all have different points in which they start to feather back their energy. So in this case it's 600 kilowatts. So just thought you might find it interesting to see the power curves for very large wind turbines. Here's a wind turbine students built from scratch, and we have all the materials actually to go ahead and build another one of these. And this used to power our offices and our classrooms in the old building. We've seen that. So some of the applications are water pumping. We can pump water directly without changing the electricity into the wind power into electricity. We can just use the rotating energy of the shaft to pump water or to compress air. We can supplement grid power by being connected to the grid and pump power back to the utility. We can be completely independent of the grid, and those just gives you some ideas of the size of the different turbines and those kinds of things. So another thing to talk about in siting wind turbines, and we're going to have a lecture next week on siting wind turbines, is that you got to put it in a space where there's what's called clean air. Now, air near the surface of the ground is very turbulent. Think about water flowing in the stream as it flows around rocks and obstructions and all the eddies and whirlpools and things that happen. That's what's happening in the air. You can't see it. But when an air hits an obstruction, for example, like this house, it starts to have turbulence before the house up to 2 times the height of the obstruction upwind, and up to 20 times the height of the obstruction downwind before the wind becomes clear again. So it's important. The typical rule of thumb for small wind turbines is 50 feet taller than anything within 300 feet distance in every direction. And so you can see that the region of highly turbulent flow extends, for 18 times the height obstruction downwind. So it's got quite a large area where there's an effect. So what this means, another thing to think about is as wind flows across the ground, there's friction. The friction of the wind dragging across the ground slows the wind down. So the wind closer to the ground has a slower wind speed than the wind high up. And it can be quite marked effect. You go up even 20 or 50 feet, you can get 2 or 3 times more 2 or 3 miles per hour more wind speed, and you can double the output of a system just by going up another 50 or 30 feet. And so tower height is really the most important determinant of success of a wind turbine, and fresh clean air that's reaching the turbine is very important. Taller is better. There are several different kinds of towers. For small wind turbines, there are tilt-down towers. In other words, towers that you can use a little winch and lower it down so you don't have to climb the tower to fix the machine if it's broken, or to install it. And then there are fixed towers, which means you can't lower them to the ground. There are towers that use guys, which are cables that go off in usually 4 directions, and those cables stabilize the wind turbine tower. And there are standalone towers that stand up on their own without the need for any cables. There are tubular towers, which are like big pipes and that's what most of the big wind turbines use these days, are these big tubular towers. And then there are lattice towers, which are a number of smaller components that are put together in kind of a lattice work. And we saw one of those in one of the earlier slides. So how do we calculate the annual energy production of a wind turbine? Well, first, you don't want to just use the average annual wind speed and multiply that times the number of hours in a year, because this is why. Let's look at, it's because the energy is related to the velocity cubed. So 10 cubed is 1,000, and 13 cubed is over 2,000. And you wouldn't even be able to notice the difference in the feel of the wind on your face if you stuck your head out of the car at 10 miles an hour and you stuck your head out of the car at 13 miles per hour. It would seem very similar. But let's look at a situation where we have... we look at the wind turbine output over 3 hours, and this is, hour 1, hour 2, and hour 3. So you have a scenario where we have in hour 1, the average wind speed was 10. In hour 2, it was 10 miles per hour for the whole hour. In hour 3, it was 10 miles per hour for the whole hour. So 10 miles per hour constant for all 3 hours. So then the average would be just 10 plus 10 plus 10, or 30 divided by 3, or 10. So, and then if we look at the kilowatt hours, let's say that it produced, at 10, the velocity cubed is around 1,000. So that's going to be 10 times 3, or 3,000 kilowatt hours, proportional to that. Now, let's look at another scenario where we have 30 miles per hour wind speed for the first hour, and then it drops to 0 for the second hour and the third hour. So if we look at the average, it's 30 divided by 3, 10 miles per hour still. But the energy was related to 30 cubed, which is 27,000. No energy the second hour and no energy the third hour, but we got a total of 27,000 kilowatt hours out of this hourly collection of wind speeds, and only 3,000 kilowatt hours out of these, even though they both have the same average wind speed. So it's not possible to directly use the average annual wind speed. So you need to do something different. So you have to look a little closer. And if you look at this is an interesting graph, and what it shows is the number of hours in the year that different wind speeds occur. So this shows that the wind speed is 0 for only 24 hours a year. It's 1 mile per hour for 276 hours of the year. Let's go down here. For 10 meters per second, it's 565 hours of the year. And so you see that it continues to go more and more hours and hours of the year, so that when you get to 9 miles per hour, it's 900 hours of the year. When you get to 6 miles per hour, it's 900 hours of the year. So most of the hours of the year, you can see the energy's here. And then as it gets faster and faster and faster, there are fewer and fewer and fewer hours. You notice 24 meters per second, there's only 1 hour in the whole year. So why would you design your turbine to operate at 24 mile per hour wind speed when you're only going to get that 1 hour a year. And if we just plot these, this is what it looks like. So it's showing you that in this case at 1 meter per second, it's somewhere around 276 hours. And then over here at 7 meters per second, it is 896. And so this is the shape. This is called a histogram, and it's showing you the shape. Now you could start to think about using this to calculate your energy, because what you could do is you could calculate the energy that your turbine would produce in each one of these bars, and you know how much energy it would produce at 2 miles per hour, 2 meters per second, let's say, and you know that operates that many hours. So there's a certain amount of energy it would operate at you would get from this mile per hour of wind, and you could calculate all those out. So let's. So where do you get this? Where do you get this information? Well, this kind of work has already been done for you in Iowa by the Iowa Energy Center, and it was done by Tom Factor, who's a long-term TM governor and a trustee of the university now, and he'll be talking to our class during this course. And he's been a large-scale wind farm developer. I think most recently he's worked for Florida Power and Light. And I think he told me once he was involved in more than $2 or $3 billion worth of wind farm development. So he's a very experienced, knowledgeable wind farm developer. And in the early part of his career, many, many years ago, he was hired by the Iowa Energy Center to develop this website. Let's go take a look at that. That calculates wind power in Iowa. So we go to the Iowa Energy Center wind website, go to the wind calculator, and they make you read this because they don't want you to take this, very rough tool and use it to make a $20 million investment in a wind farm or something. So they say that this gives you all the caveats about using this site. So we just click on that. Shows us all the counties in Iowa. Let's pick Jefferson, where we are, and then it shows all the cities in Fairfield. In Jefferson County. So let's pick Fairfield, and we can look at this the energy output for each month, an individual month, or we can look at for the whole year, which will also give us the individual months, or we can just look at the total amount for the year. And there's two different size turbines to select from, the small or the large. But let's just look at all of them. And we drop this down. This gives us a whole bunch of different manufacturer wind turbine specifications, characteristics that are built into the calculator. So let's use that Berge XL, which we have at the Sustainable Living Center. We have to tell it how tall the tower is. It's going to be an 100-foot tower. And one turbine, we'll just leave the loss factor at the default, and then let's hit the calculate button. And it's going to come back and give us the total amount of energy for the year, 16,000 kilowatt hours. And then it's going to give us the amount every month. And you can see the minimum is in August at 763, and the maximum is in January, is it around 1600, or also in December? No, excuse me, it's in March and April. It's 1800. But you notice it's fairly consistent, 14, 16, 1800 all through the winter and fall months, and fairly consistent at low output during the summer months. Let's take a look at a really big wind turbine, like one that might supply the energy for Marish University Management. Let's look at a Clipper, which was the is it here? Yeah, Clipper. This is the one that's up at and let's put it on a 300-foot tower. This is the one that's at the community college up in Cedar Rapids that many of you went to see. And let's leave all the rest of it the same. Let's put it in Fairfield, and then let's calculate that. So you can see we put out about 6 million kilowatt hours a year with that turbine, and that's more. I think MUM's annual consumption, energy usage is about 4 or 5 million kilowatt hours. So this one turbine would provide us with all of our energy, but it wouldn't necessarily provide all of it in every month. So there might be some months in the summer when we might need 600,000 or 700,000 kilowatt hours, and we only get 400,000 from the wind turbine. and some months in the winter where maybe we only need 500,000 kilowatt hours, but we're getting 600. So we could, if we're able to put this energy out to the grid and get credit for it, and that we could use to offset our summer usage, then this could make sense. And that's in fact what they do at the community college, at Kirkwood Community College. So that's using the Iowa Energy Center website. You can also collect wind data over a long period of time, and then there's methods for taking that individual wind data you collect for 1 year and making it so that it's more generally applicable to multiple years or a typical meteorological year. You have to correct for the anemometer height. In other words, the wind power changes. So if you're collecting energy, the wind data at 100 feet and your turbine's at 300 feet, there's formulas you can use to adjust for anemometer height. You can get a histogram of wind speeds, which we looked at earlier, which is the wind speed in the hours that it's equal to or exceeded. And then there's a shortcut capacity factor. So we'll look at a couple of those methods. So here's a couple of wind turbine design considerations. You have to think about the high wind survival strategy. Are you going to change the blade pitch? Are you going to feather the blades so that the wind just flows through them rather than having them catch the wind like you would if you were rowing a boat? You can have the oars dig into the water. If you tip them at an angle, they'll just skim through the water and not actually do anything. You can rotate the whole machine away from the wind, and this is what the Berge wind turbine does that we have. And then once you're surviving by getting rid of that wind, if you want to actually shut it off, how do you shut it off? You can have an electric brake, a mechanical brake, and you can manually rotate the machine out of the wind. It often doesn't work to have a wind turbine at full power output and then throw a brake on. You have to disengage the wind turbine from the flow of wind, because if you just put the brake on, it's like driving down the freeway at 100 miles an hour with your foot on the gas, leaving your foot on the gas and trying to slam on the brakes at the same time. So you need to get that energy away from the turbine before you throw the brake on. The types of governors, there are DC, just got types of generators. There are direct current generators, alternating current generators, generators that use permanent magnets, generators that have a magnetic field that's created in some other way than with a permanent magnet. And how does it automatically face the wind? How does it turn? This is called the yaw control. Is it upwind? In other words, is it upwind of the tower? Does the wind hit the blades first and then hit the tower, or is it downwind? Those are all design considerations when you're looking at a wind turbine. System design considerations: is it going to be a grid tied or is it going to be off grid? If it's grid tied, is it going to be batteries or grid tie only? We have a grid tie only wind turbine at the Sustainable Living Center. If it's off grid, you have to look at what's the system voltage going to be. Is it going to be 12, 24, 48? What battery capacity you need? What inverter do you need? What kind of monitoring and metering? What's the distance from the wind generator to the power use? What are the wire sizes you need? All those are things that you would consider in a design of a system. So let's take a look at a case study here. This is the SkyStream wind turbine. Used to be made by a company called Southwest Wind Power. They went out of business, but another company bought them up, and that's a problem with small wind turbines. No one company has made very many except Berge, so a lot of the wind turbines that were built were sort of prototypes and had reliability problems, and manufacturers go out of business. SkyStream was actually, they built quite a few of these, and they fairly reliable, but unfortunately a lot of them were put on very short towers, and the customers were very disappointed with the output of them. This machine has 12-foot diameter blades, and it produces 1,800 watts in a 20 mile per hour wind. Another unusual feature of this wind turbine, a couple unusual features. One is that it's actually downwind of the tower, so the wind is flowing this way. It goes through the tower and then comes to the blades, so it doesn't face upwind to the flow of wind, upwind of the tower. Which can cause some problems with what's called tower shadow. So when the wind's flowing this way into the turbine and hitting this tower, it's going to be blocked. The tower's going to block the wind. So as the blades go around, they're going to hit this area where there's very little, where the wind speed's much lower. It can cause some vibration. It's not a problem in the SkyStream, but it can be a problem with other turbines. Another interesting and unusual thing is all the controls and the inverter and everything that's needed to connect this to the grid are actually located at the top of the pole in this nacelle. That's what the covering for the generator and all the electronics is called in a wind turbine, the nacelle. And what that does is then all you have to do is run a wire down this pole into your house and plug it into a circuit breaker, because all the electronics and controls are actually in the turbine. And it will produce about 400 kilowatt hours per month and a modest wind speed, which is half of what a typical homeowner might use. Here's the installation sequence. It's a sort of a tilt-up situation where you build a foundation for the tower. Tower lays down. You put up what's called a gin pole. Here's a gin pole. Connect a cable, and then it goes up here to the gin pole, and you pull it with some device, a truck or a winch, and it lifts the turbine and tower up until it's directly upright, and then you can bolt it down. And then it's just a matter of running the wire inside to the circuit breaker panel and producing, and then you can start to produce power, because all the electronics and controls are on top of the tower. There's a whole subculture of people who build home-built machines. We saw this one earlier from the Sustainable Living Center. From the old building. And this is a group of students who. Let me see. I'm going to get rid of that. This is a group of students. This guy, Julian Potter, his daughter might still be. His sister might still be at school here, but he was a really bright student, and he really got into figuring out the number of coils of wire and the strength of the magnets and all that kind of thing, and built a wind generator from scratch. And he used an open source design made by an organization called Other Power. And I kind of discouraged him from this, because typically in the past, home-built wind generators have been, really troublesome. But this open source design, because there are hundreds of people all around the world who work to make it better, actually works pretty good. And there's a little video of this project of them building this wind turbine, and we still have it around. We could put it up. It's also pretty fun to just carve a set of blades, and if we got a windy day, we'll take one out. Many of the students in the previous course that are in this course saw somebody flying that. And Julian went on to get a master's degree in architecture, and then he went on to start a sustainable living program similar to ours on the West Coast up near Oregon. I'm not sure that's still operating, but it was quite a job. I helped him with it a little bit. He consulted with us on getting his program started. And now he's doing an eco-village project in addition to the university he was starting. So how much energy do you need? First, to figure the cost, you have to figure out how much energy you need. So a typical home uses 800 to 1,000 kilowatt hours. Homes in Abundance Eco-Village, they keep their showers hot and their sodas cold, but they only do it with only 100 kilowatt hours per month. So again, the cost will depend a lot on how efficiently you use energy. This is quite inexpensive to supply, and this could be quite expensive to supply. Very small systems. So let's look at a couple of different size systems and see how much they cost. If you have a small cabin or a boat and you only need, say, 10 to 20 kilowatt hours a month to run a couple of lights and a stereo, then you might put in a 4-foot diameter rotor that only puts about 300 to 400 watts out on a maybe a 50 or 60 foot tower or something like that. And something like that could cost as little as $1,000 to $2,000. And an example of a commercial machine is the Southwest Wind Power Air. And again, Southwest Wind Power is out of business, but somebody still makes the Air and the Air Breeze. And they've sold over 100,000 of these units. But really, they don't, 10 to 20 kilowatt hours a month is not a very much high percentage of the 800 to 1,000 kilowatt hours you use in a typical home. So if you put one of these on your house and think it was going to supply all your energy, you'd be quite disappointed. But if you have a small, modest requirement for energy and you have a good wind site, these can work. Then a medium system would be grid-tied or off-grid, 100 to 400 kilowatt hours a month in an efficient conventional home. It might have a 12 to 18 foot blade diameter and a generator size of 2 to 5 kilowatts. An example is this Southwest Wind Power Skystream we saw earlier. It has 12 foot diameter blades, 1800 watt system, $12,000 to $20,000 for those systems. Then a very large system, which could provide enough energy for one or several, large energy inefficient homes, that would have an 18 to 30 foot blade diameter, 5 to 20 kilowatt generator. And an example would be the Berge XL that we have here at the Sustainable Living Center with a 22 foot diameter blade. And that's about $35,000. Actually, that's for the cost of the tower, and the turbine, probably the install cost is more like $50,000. We talk about bird mortality a little bit, and wind turbines do kill birds occasionally, and they have to be sited properly. But even poorly sited wind turbines kill very few birds compared to how many birds are killed by other things, like buildings and windows kill 500 million birds a year in this country. Cats kill 100 million birds, and wind turbines kill a few tens of thousands of birds. And if you look at the aesthetics of wind, people are concerned. They don't want to look at that. But this is the aesthetics of centralized power systems, where we have to build these big power lines that go all across the landscape. And people are used to this aesthetic. They don't complain about it too much. But I don't find that. I find that much less attractive than to see a wind turbine which is spinning in relationship to the energy that's flowing across the earth, and providing me with clean energy. I appreciate that aesthetic of that rotating wind turbine. So we talked a little bit earlier about the V cubed problem, and I think we already went through this, where we looked at what's the situation. 10 hours of a wind blows 10 hours at 8 meters per second, at 10 hours at 4 meters per second. So at 10 hours at 8 meters per second, it's going to produce this is per meter squared. So to get the total energy for a wind turbine, you'd multiply this by how many meters the circle was of the diameter of the circle that the blades make. And so at 8 meters per second, it's going to produce this amount per meter, and at 3,000. And at 4 meters per second, it's only going to produce 400. And so the total is 3582, but most of that was produced in the 10 hours the wind was 8 meters per second. So notice how insignificant the energy contributed by those low-speed 4 meters per second wind is. So a lot of wind turbine manufacturers will brag about how their wind machine will start to produce energy at 2 or 3 meters per second, whereas maybe the competitor doesn't produce till 4. But it doesn't really matter, because there's just not much. Even if there are many hours at that wind speed, there's just not much energy available in that wind speed. And again, this is showing what happens if you just plug in the average. You would get a very different and wrong amount of energy. So let's skip that. Skip that. Let's see. So what are we looking at here? We're looking at how much energy there is between 4 and 8 miles per hour compared to between 15 and 19 miles per hour, looking at using the Berge wind power curve. So if we looked at 4 meters per second wind velocity, and the power is 500 watts. Let me see what's going on here. Well, so what this is showing is that with the Berge, with the wind between 4 and 8 miles per hour, you've got about 500 kilowatt hours that were produced. But when the wind is between 15 and 19 miles per hour, 19 meters per second, you've got about 12,000 kilowatt hours produced. So again, here another way to think of this: 8 times, double the wind speed, get 8 times the power. These are equal amounts of energy. 1 hour of wind at 20 miles per hour, 8 hours of wind at 10 miles per hour, and 64 hours of wind at 5 miles per hour are all equal amounts of energy. So here's another way of looking at the this is another, never mind, we'll just skip through this. We've looked at this before. I think this has been getting to be a long lecture. I think we'll quit. There's another way of calculating the total amount of energy that's available that's based on the mathematical shape of this curve, which is this is the wind speed probability density function. What this is saying is that this is the wait, let's see. Let's look at this. So, so this is the percent of time that the wind is at each one of these wind speeds. And this is in miles per hour at the top and meters per second. So what it's saying is that, 12% of the time the wind is at, around, 12 meters per second, 12 miles per hour. And at 4% of the time, the wind is at maybe 25 miles per hour. So just showing you that most of the energy in the wind is right here. And so this is what's called, this particular curve is what's called a Rayleigh curve distribution. So this particular shape is called a Rayleigh curve, and this is the actual shape of the wind at Altamont Pass. And you see it kind of approximates this, even though it's off just a little bit there. And so it turns out that a lot of wind probability density functions, which is this curve that shows you what percentage of time the wind is at each different wind speeds throughout the year, that probability distribution curve has a Rayleigh, or close to a Rayleigh distribution. And then there's people we won't do it here, but there's ways in which you can prove that the average power, if it's a Rayleigh distribution, is 1.95 times a half times the density times the average wind speed. And so in this case, you can get the average power from the average wind speed using this formula, assuming that it has a Rayleigh distribution. And so if you've got, in this case then, if you've got a 7 meter per second average wind speed at 125 feet, the average power in the wind is 400 watts per square meter. And you can just get the total power by multiplying that times the number of square meters you have that the rotor diameter is catching from the wind, and then multiply that times the number of hours in a year, and you'll get the total energy, an estimate of the total energy because of this Rayleigh distribution. But you have to use this formula to calculate the average power.